Okay, let's take a look at some of the problems from the Alkanes exam from last year. So, looking at the first page, let's think about these chemical formula. We shouldn't need any preamble or introduction. It should be straightforward, these line angle formulas. So C3H4, for the first one, it's an alkyne molecule. Second one, which is an enol derivative, formula C4H8O. That second one. Then an alkane with a cycle, cutting the hydrogen count down by 2, C8H16. Then the last one, we have a cycle and some alkene bonds in there, which cuts the hydrogen count down. So C9H12. Now for the name of the molecules, we'll do one or two. I think these are probably the two more interesting ones anyway. And looking for the longest chain of carbons, we have 1, 2, 3, 4, 5, 6, 7, 8 carbons in total. As we'll look at the possible position of branches, lowest possible numbering is in this direction here. And it gives us a couple of branches, a fluorine branch, a methyl, a second fluorine, and then a 1,2 ethyl branch. So the core name of the molecule is the fact that it's a octane derivative, if I write it down there at the bottom. And we've got some branching, and we'll number the branches as a 2,4 difluoro branch, a 5 ethyl branch, and a 3 methyl branch. But we'll list them in the name in alphabetical order. So first part to this puzzle is the fact that we've got E for ethyl, so 5 ethyl. The second part of the conundrum is the F for fluoro, so it becomes 2, 4 difluoro. And then the last part, of course, is we have the M for methyl, so 3 methyl. So the whole name for this molecule is 5 ethyl 2,4 difluoro 3 methyl octane. Looking at the example on the right hand side of the page, we've got 3 rings connected together, but the largest of the 3 rings and dominating the molecule is this middle cyclohexane ring. So that gives us the core of the name. It's a cyclohexane molecule. And we have 2 cycles branching off from this central 6-membered ring. We have a butyl 4-membered ring and also a pentyl membered ring. So it's going to be 1 free substitution, but is it 1 pentyl or 1 butyl? We go by the alphabetical ordering of the 2 branches, with the 1 and 3 positions being the same either way round. So we're going to number the first carbon from this point here, which gives us 1 cyclobutyl, 3 cyclopentyl, cyclohexane. 1 cyclobutyl, 3 cyclopentyl, cyclohexane. Just rolls off the tongue. Okay, look at some extra problems. I don't think we need to worry about the extra ones here. I'll leave that to yourself for some excitement. When we're drawing these line angle formulas, again we'll work backwards from the name. So primarily it's a octane molecule. So we need 8 carbons in the maiden chain. So 1, 2, 3, 4, 5, 6, 7, 8 carbons long. And if we assume this is carbon number 1, we'll build on it from this side. So there's 1,1,1 trichloro substitution from this point. Chlorine 3 times over, And we also have a 3-isopropyl substitution in this third carbon here. And this is one of the older names we said for a propane substitution, but it's connected to the main chain through the second carbon. The second molecule, again building backwards, we have heptane for the main chain, which is 7 carbons long. So 1, 2, 3, 4, 5, 6, 7. And we've got a couple of branches on the molecule again. First one, the 1-fluoro substitution on carbon 1. And also on the third carbon, we have a branch, we have a cyclopentyl branch. So 5 carbons in that branch, connecting it to the main chain. And that gives us a second named molecule in its picture. Now, defining stereoisomers, we have the same formula for stereoisomers. We also have the same connectivity. So no change there so far, but the difference is that we have different orientations or different positions for the atoms. So these were our special isomers where perhaps the branches were aligned in a different fashion, but still connected to the same atoms. So this is when we were talking about our cis and trans kinds of isomers. Moving on to the next page. The constitutional isomers of this bromocyclohexane. This time we've got a bit more freedom. We can change the connectivity with the constitutional isomers as long as the chemical formula remains the same. So the easiest thing to do to mix things up is start drawing examples with a 5-membered carbon ring, which then gives us a carbon as a branch, and we can add on the bromine somewhere nearby. It could be on adjacent carbons, or we could spread them out a bit. A 1-free substitution. We could even have them on the exact same carbon. We could even go down to 4 carbons in the main cycle and have 2 methyl groups and a bromine substitution. We could put them in different positions, and there's lots of variations. Or we could even have 1 ethyl branch and the bromine attached. Or we could draw a 4-membered ring and have that ethyl branch and then put the bromine branch on the ethyl branch. Put it on the first carbon or maybe even on the second. So there's lots of variations to be had. We even go down to a 3-membered cyclopropane ring, and then we'd need 3 carbons branching off from the ring, and of course the bromine itself. Could have more methyl branches on the 1 carbon, or maybe even a propyl branch coming off that triangular ring, and then the bromine positioned around about, or perhaps on that propyl branch as well. So there's quite literally lots of combinations for this particular one, but as long as you gave 4, that was fine. For the naming of the functional groups, we have this carbon to oxygen double bonded group, but it's on the end of the molecule, and this was our aldehydes. Silence when I'm filming. Local wildlife in this place. Of course, if the carbon to oxygen double bond was surrounded by carbons on either side, that would be a ketone. With the nitrogen in the molecule, this is one of our amine functional groups. And then the last one with our oxygen to hydrogen bond in the molecule. This was of course, an example of our alcohol. Okay. Last molecule. This is perhaps one we've done before, but let's have a look at it anyway. We're looking along that carbon 2 to carbon 3 bond in this butane molecule, and we're going to draw the low energy and the high energy conformations. So for the low, it ultimately means that we have a staggered conformation to keep those bonding electrons as far apart as possible. So for the near side carbon, carbon number 2, we have carbon number 1, which is a CH3 group, and also the methyl branch. And likewise on the carbon behind, carbon number 3, it has a hydrogen and 2 CH3 groups. Now if we want it to be as low in energy as possible, the one thing we want to avoid is putting a CH3 group there. So let's put the hydrogen there. If we put the CH3 group here, then we get 2 gauche strains in between that position. So the hydrogen there, and it puts our CH3 groups like this. And therefore, for the strain energy, which is gauche strain every time, there's one there, there's one there, and that's about it. Nothing there, nothing there. So there's 2 examples of 3.8 kilojoules per mole. And that gives us strain energy, if my brain is working properly, of 7.6 kilojoules per mole for those 2. And that's the lowest energy conformation possible for this molecule. So the highest energy, this time, we're looking at the groups when we have eclipsing of the atoms behind each other. So the highest possible one, we put CH3 to CH3, CH3 to CH3, and then hydrogen to hydrogen. So lots of strain energy here for the CH3 to CH3 groups. Of course, that was one of our worst ones, which was 11 kilojoules per mole. Another 11 kilojoules per mole. And then a hydrogen to hydrogen one here was, of course, for that eclipsed. That was a much more reasonable 4 kilojoules per mole. So that gives a total of 26 for the second conformation. So 7.6 compared to 26. And don't forget, don't work too hard this week. Give yourself a break now and again just to get away from the chemistry.